Okay, so good morning, everyone. This is Li Lu. Today, I'm going to talk about key aspects of marine processing technology. Here is my talk outline. First, I will start with some introduction. Then we'll mainly focus on to highlight the marine processing technology, including source-based signature, broadband processing, noise suppression, and multiple suppression. Then conclude with showing some real data example. This is a conventional marine seismic acquisition. So we can see a seismic vessel towed 2 sources and 6 cables. Normally, these cables may be from 6 kilometers long. Right now, maybe can extend to 18 kilometers long. And this definitely more complex than what we are looking at. It has very accurate position, support system, make sure all the source and the cables are at right position. So unlike the land acquisition, marine acquisition use air guns to generate the pressure wave field and use the streamers of hydrophones to record this pressure wave field. So definitely it's different from land processing, although it won't have some surface consistent problem or noise issues. So definitely the marine processing workflow will tackle different problems. So this is a general processing flow that include starting from import data to some wavelet processing, including the source-based signature, followed by some tidal statics or water column statics, and then do some noise attenuation. And one of the key processing is multiple suppression. And in the end, of course, including the imaging for PSTM imaging and the PSDM imaging. So I'm not going to talk about this in detail, but we'll highlight some marine processing key aspects. So source-based signature, broadband processing, noise suppression, and the multiple suppression. So because the marine acquisition uses this air gun, so when a shot is fired from this air gun below the water, a pocket of air is created. So this pocket of air will begin to expand or contract. So as it moves towards the surface of water. So this expansion and the contraction of this pocket of air can be considered as a second energy source. So this energy is recorded and can be seen in this amplitude spectrum in this low frequency portion, this undulation. One of the advantage for the marine processing is the marine processing can do some deterministic decon, unlike the statistic decon in the land processing, because the marine have this source wavelet available. So this picture shows the typical source wavelet with the primary up front and followed by a bubble with time delay. So the source wavelet can be obtained from this nucleus model. So this wavelet will be provided by the boat, but sometimes the bubble may be not modeled properly. And in the modern acquisition, and also it will derive from the near field recording. So this allows us to do some shot by shot source-based signature. And if we don't have any source wavelet provided by client, sometimes the processor will extract the source signature from the data, but this only works when the water bottom is deep enough. And sometimes this kind of method has some disadvantage is the wavelet will be polluted by the near surface geology. So the source-based signature, you can see, right? That means we do some inverse filter to do the debubble, get rid of the Bible in this wavelet trail. And the other important thing is to do the zero phasing. So the interpreter will like the zero phased sentinel wavelet that will give better resolution. So here I'm going to show some data examples for the source designature. This is the near channel before the debubble. This is the near channel after debubble, before and after. So this shadow, you can see this shadow with the period maybe more than 200, maybe 260 milliseconds. So it's get rid of it. And how it looks like in the amplitude spectrum. So this undulation before the debubble is in red, and after doing the debubble, you can see it is much smoother in the low end of this frequency spectrum. The debubble is one part. The other important part is zero defacing. So look at this water bottom is a kind of minimum phase. So after we do the zero phasing, we can see the wavelet becomes more symmetric, and this peak is line. We can see if I toggle this one, the peak line up with the onset. So the before defacing, this is onset. After zero defacing, this becomes the peak. Yeah, one of the phenomenon for the maroon acquisition is this source and the receiver ghost. So normally the source and the receiver will be several meters below this water. So when a shot is fired, the second wave will propagate to all the directions. So when it's propagated to the air water surface, then reflect back, this generates the ghost, because the air and water surface has the reflection coefficient is equal almost near to -1. So from the wavelet, you can see this primary in the blue will followed by a similar wavelet, but with the opposite polarity. So the same thing will happen to the receiver side. This kind of source and receiver ghost will have the destructive effect on the amplitude spectrum. We can see this notch frequency on this amplitude spectrum. So without any ghost, we can see this white flat spectrum in blue. And with all these ghosts, we can see this notch frequency corresponding to different source and receiver depths. Definitely, this will narrow the bandwidth and influence the resolution of the seismic section. So we have to deal with it. So the deghosting we do here is using the pre-migration topic domain deghosting. So an optimal notch filter is found by researching of the time delay of the ghost for each P traces. So this method can handle the space and the time variant feature of the ghost. And Juefu also implement this greedy redown transform. And as he talked yesterday, although it's using in a different domain, different method, but it will enhance the topic domain resolution. So this will result in handling spatial editing well. If we look at the water bottom wavelet before deghosting, so this is the water bottom, and the cartoon shows this left top corner shows the repass for the primary in blue and the source ghost in green, the receiver ghost in red, and source and receiver ghost in pink. So looking at the water bottom in this seismic, so we can see this first trough is the primary corresponding to this blue repass, and this peak in red corresponding to the green source ghost and the red receiver ghost. Below this red peak is another trough. Why is a trough? Because it's reflect twice, right? So on both source side and receiver side, so -1 becomes the positive. So we have to deal with the source ghost and the receiver ghost. So this is the shot gather before we do the ghost. And if we do the receiver ghost, the half of the wavelength is removed. That means the receiver ghost is removed. And if we do both shot and receiver ghost, we can see another half of wavelength removed. And on the cartoon, you can see only the primary in blue repass left. So if we QC, this is different QC method. Why is QC when put the datum at the cable? So if we QC the datum at the sea level, shot gather without the ghost and with both at the receiver the ghost, what we can observe is the side lobe was reduced and wavelength definitely sharpened. So look at the PSTM stack that will demonstrate more the effect for the ghosting. So this PSTM stack without the ghost, looking at this water bottom area, we can see trough, peak, trough. And if we do the deghosting, so this deghosting sharpens the wavelength. We don't have any side lobe anymore. And it will broaden the amplitude spectrum. So look at this amplitude spectrum. The black is the spectrum before the deghost. The red is the spectrum after deghost. So we can see this deghosting broaden the spectrum on both low end and high end, and this notch frequency was nicely removed. So the amplitude spectrum become more wide. Yeah, from this example, we can see definitely we get a lot of benefits from deghosting. So it reduces the side lobes on the seismic wavelength. This results in higher resolution, and it broadens bandwidth and improve the signal to noise ratio. It will help to improve the velocity analysis. Definitely is beneficial for the interpretation of the geological structure. Yeah, then we go to the noise suppression. So the in the marine acquisition environment, it has the different kind of noise, maybe the swell noise, the seismic interference, etc. Of course, it also have these two category noise, linear noise or random and erratic noise. Like the Dennis presented yesterday, Absolute have these kind of tools to handle it. So we have the eigen image filter, SWANA, coherent noise attenuation CNA, TF suppress. This is the raw shot from the acquisition. So it covers by the DC component and the swell noise. We cannot see any seismic event. And after we doing this DC component and swell noise attenuation, we can see nicely all these primary was brought out. But we still have this first break on this far offset direct arrival. So we need to do some direct arrival suppression. On the far offset, we can see this reflection coming up nicely. If we QC in the CP domain, this is the before direct arrival suppression. This is the after direct arrival suppression. So this far far offset information is very important for the estimation of some, for example, the TTI, anisotropic parameters, and also is good for the AVO analysis. The other kind of noise in the, especially in the conventional seismic acquisition, is this seismic interference noise. You can see it appears as hyperbolic, linear, hyperbolic coherent noise. It's not easy to tackle in this short domain, but it can be resolved in a different domain. So what we do is we randomize in the common channel domain. So this kind of noise become more isolated and stand out. Then we do some FX media filter, it will be get rid of it. This is another OBC example. We're using the Kazal random noise attenuation. So we get the left panel is the before noise attenuation, the middle is the output from the noise attenuation, and the difference on the right. So this after the noise attenuation, we can see this seismic event more clearly, and we don't see any very little leakage on this difference. Yeah, one of the important tasks for the marine processing is to do the multiple suppression. So as Jeff talked about yesterday, we have this data-driven multiple model prediction method. We also have some model-driven method. So we have this MWD, based water layer related multiple. We have Srme, surface related multiple elimination. For the interbed multiples, we have IME and ISS, and also different redown parameters. So Srme, if we talk about Srme versus MWD, both are data-driven, so not rely on the velocity difference between the primaries and the multiples. So Srme can model more types of surface-related multiples, but it needs good sampling of the near offset. And MWD has lower requirements of the near offset sampling, but it needs good knowledge of water bottom. And MWD don't have this crosstalk issue as Srme because it uses the green function. So to do a good job on the multiple attenuation, we need to have a good processing flow. It normally involves 3 steps. First, we have to precondition the data, including to do the noise attenuation, to do interpolation, regularization, to have well-populated input for the multiple model prediction. Then after the multiple model prediction, we need to do a good subtraction. This has some different methods available. I'm going to give you some data examples on the MWD and Srme. So this is the near channel before the MWD, and we can see this definitely is contaminated by all these high order regression of the water layer multiples and different kind of maybe even have the peg leg and all these kind of multiples on top of the primary. So after MWD, we can see the underneath primary is coming out. And this section will be more interpretable for the interpreter. So this example for Srme, this stack before the Srme, this is the stack after Srme. Although we apply this data-driven method, multiple attenuation, we still typically we still have multiple left. So the read-down is a very routine processing step. So we have different algorithms available. So the conventional high resolution read-down, and we have the high peering read-down, and also GIF's greedy read-down. So these definitely the greedy read-down will give us more high resolution topi model, and it has better separation between the primary and multiples. This is the example after the migration. So it's the PSTM 6 gathers. And before the read-down, we can see the residual multiples still left after we do a lot of steps, multiple condition before migration. And we also see the noise. And it looks pretty dirty. But if we run that read-down, actually this one is greedy read-down, and the data become very clean, and you can see this seismic event from the near to far. It looks pretty natural, and this we measured AVO curve, and this AVO curve was preserved very nicely. So this is before and after. The last example is the combination of all these methods together that include the Srme, read-down, and some methodology for the diffracted multiple suppression. So this is the example from a very robust water bottom. So this kind of undulation of water bottom will generate some these diffracted multiples, which is much more difficult to get rid of it. And after all these methods together, the multiple was attenuated nicely, and the seismic event you can see is coming out and looks very interpretable right now. Before it's all covered by all these multiples. If we look at the shots without any multiple applied, so these kind of apex shifted multiples also it is difficult to be tackled. And with this combination of the multiple suppression, so it was removed nicely. Yeah, so with all these methods introduced, finally, I'm going to show you some image comparison between the legacy and the absolute new processing image. So this is the 2022 legacy PSTM stack. What we see is we have all these noise on top of all the primaries, and if we look at our newly processed PSTM stack, actually this was processed last year, 2020. We can see more sharper fault plane and more clearer BSR. This is a bottom simulated reflection. So which the client is looking for, and before and after. So not only we have the higher signal to noise ratio, but also better imaging everywhere. So if you look at all this area highlighted in this blue. Another example, also we processed in last year. So this is a legacy PSTM stack. And this seismic data was acquired in 1975. It's pretty old, almost 40 years. So the acquisition has the source and the receiver interval is 50 meters, very coarse grid, and also have very shorter offset range from 300 meters and to 2,800 meters. So we lack of the near offset and also don't have the longer offset. definitely this poses great challenges in for the processing. So this is the legacy PSTM stack. This is the absolute new PSTM image. So look at this Seismic new PSTM stack. It has improvement in several aspects, including the better imaging highlighted in the orange, better demultiple colored in blue, and better resolution in green. So if I could draw your attention to the area highlighted in this orange area, for example, so the old processing has difficulties to balance multiple attenuation in preserving the primary and attenuate the multiples. The new processing have this seismic events more continuous and sharper, has the high resolution there. So we can see the modern marine processing technology definitely has strong capacity in handling this old acquisition data and to provide a much better resolution seismic image. Yeah, this is the end of my talk. So any questions?
Thank you very much, Lee. Much appreciated. Very good presentation. Very interesting. Si alguna pregunta al momento, por favor, compartirla por el chat o activar sus micrófonos. Tenemos una pregunta. There is a question from Jose. Can I remove the ghost after stack?
No. So for the after the stack, as I showed in the algorithm here, the method we performed in the topic domain. So it is in it's applied in the short domain, and from the short we need to transform the data to the topic domain. And in the topic domain, we search optimal notch filter for the different P. So even you look at the XT domain short gathers. So for the near middle far, it has different ghosts. From the shallow to deep, it has different ghosts. So the ghosting will honor the spatial and the time variant feature of the ghost. So to answer your question, is no.
Thank you, Lee. Si responde la pregunta, José, o tienes más información, ¿quieres ampliarla? Gracias. Si hay más preguntas, bienvenidos. Si hay algún tema específico que quisieran revisar, en algún proyecto piloto, hacer una prueba, por favor, también con gusto nos contactan. Como mencionábamos, Absolute Imagine tiene amplia experiencia en distintos proyectos en distintas cuencas en Colombia, de manera que no somos los retos que hay en Colombia. Hay otra pregunta. Another question, Lee. How do we remove the direct wave?
Okay, let me. You mean this part, right? Yeah, this direct arrival suppression is not like a program, but it's kind of methodology. So it's a different steps. So what we do is we model this direct arrival in the topic domain, and we subtract it in the topic domain, then convert back to the xt domain. So it's kind of a processing flow using some, so for example, if this direct arrival has certain velocity range, right? If we say from 1500 to 1800 in the topic domain, it will appear in the certain range of the P. And after we get, we model it, we transform back to the time domain, then we subtract it. So it's a combination of different modules together. Right, answer your question?